In the depths of darkness, the mystery of the black hole. Within the cosmic ripples, time's waves ceaselessly roll. A place where light is trapped and sound is lost. In the heart of that darkness, the flame of theories exhaust. Beyond the horizon, where space and time entwine. When the doorway to time opens, past and future align. As starlight races through the tunnels of time, the night sky of yesteryear unfolds in sublime. The heralds of the future seep through the cracks. Traces of destinies foretelling, mysteries from the tracks. The enigma of the cosmos, the song of the blue planet. Whispers of the stars, the secrets time can't forget. Journeying at the speed of light, a cosmic existence. Dancing through the ages, the universe's heartbeat's persistence. Entwined in the threads of fate we find. Flowing through the cosmos, the ever-expanding time. The pupil of the black hole, the gateway to time travel. Captivated by those mysteries, we run towards dreams unravel. Today, we will serialize the 16th lecture of the introductory course on astronomy, covering black holes and time travel in 3 parts. Subscriptions, likes, and notification settings greatly support video production. The concept of a wormhole, referred to as a bug hole in Dr. Stephen Hawking's writings, is a hypothetical concept based on Einstein's general theory of relativity. According to Einstein's theory, gravity represents the curvature of spacetime. Therefore, in regions of strong gravity, spacetime is warped. If spacetime is warped enough, it may give rise to a wormhole, connecting 2 distinct spaces. A wormhole, or bug hole, is a narrow and elongated passage connecting 2 points in space. Similar to a bug traversing an apple and reaching the other side faster than going around the surface, a wormhole might allow transcending time and space more efficiently. Dr. Hawking explained the concept of bug holes in his book A Brief History of Time. According to Einstein's general theory of relativity, strong gravity corresponds to the curvature of spacetime. In quantum mechanics, spacetime is quantized, composed of continuously small particles. Bug holes could be explained by combining these 2 theories. If the curvature of spacetime between 2 spaces is significantly warped, and this curvature is smaller than the size of quantized particles, a bug hole connecting the 2 spaces could form. Dr. Hawking suggested several possibilities if bug holes exist. Travel to other universes. Aid in understanding the origin of the universe. Possibility of time travel, travel to the past or future through bug holes. Possibility of interstellar travel, travel to other universes through bug holes. Movement of energy and matter, transfer of energy and matter through bug holes. Dr. Hawking also proposed that bug holes could open up the possibility of time travel. If one could travel to the past or future through bug holes, time travel becomes feasible. However, the existence of bug holes remains a theoretical hypothesis. If bug holes were to exist, they would need to satisfy 3 conditions. Sufficient warping of spacetime. Stability of the entrance and exit of the wormhole. Ability for matter to traverse through the wormhole. Connecting 2 distant spaces. Can occur in regions with strong spacetime curvature. May open up the possibility of time travel. Nevertheless, the existence of bug holes has not been experimentally verified, and many aspects of their characteristics remain unknown. While Dr. Hawking opened up the possibility of the existence of wormholes, he also issued a warning about their potential dangers. If one were to travel to another universe through a wormhole, there is a risk of not adapting to the laws and life forms of that universe, leading to potential hazards. Additionally, altering past events through time travel could result in unforeseen consequences in the present and future. In conclusion, wormholes are a fascinating concept with the potential to exist in the universe, but their associated risks should be carefully considered. Dr. Hawking emphasized the need for caution when exploring the possibilities offered by wormholes. The existence of wormholes remains a mystery, but it is anticipated that, if proven, they could play a crucial role in advancing our understanding of the universe. In black hole theory, the event horizon refers to the region surrounding the singularity at the center of a black hole. Crossing this region means reaching a point where not even light can escape from the black hole. The event horizon determines the size and shape of the black hole, varying based on its mass, charge, and angular momentum. The information paradox in black hole theory arises when applying both general relativity and quantum mechanics simultaneously. It revolves around the question of whether information about the matter consumed by a black hole is forever lost or preserved in some way. According to general relativity, a black hole, as per the no-hair theorem, carries no information except for its mass, charge, and angular momentum. Consequently, it should emit Hawking radiation unrelated to the initial state of the ingested matter, eventually evaporating. In this scenario, information about the consumed matter appears to be permanently lost. However, according to quantum mechanics, the state of a physical system is determined by a unitary operator, and since unitary operators have inverse operators, information must always be conserved. This implies that information about matter consumed by a black hole should somehow be encoded in the radiation emitted by the black hole. The conflict between these two theories results in the information paradox, a major topic in the field of black hole thermodynamics. Various solutions have been proposed, such as attempts to prove information preservation through the holographic principle or AD/CFT correspondence. Black hole theory remains an incomplete field requiring further research and discoveries. I will now explain the holographic principle and AD/CFT duality related to black hole thermodynamics. The holographic principle suggests that information about the volume of space can be encoded on the boundary, such as the gravitational horizon of that space. This principle originates from the Bekenstein-Hawking formula, stating that the entropy of a black hole is proportional to the area of its event horizon. This implies that information about the objects consumed by a black hole is encoded on the surface of its event horizon. The density of this information surface is limited to Planck units, known as Planck bits. AD/CFT duality posits an equivalence between a reduced string theory in anti-de Sitter space, ADS, and a conformal field theory, CFT, at the boundary of that ADS space. This duality provides a non-perturbative formulation of string theory and is considered a significant development in both string theory and quantum gravity. The utility of this duality lies primarily in strong/weak duality pairs, making it mathematically more manageable when quantum field theory's strong interactions correspond to the weak interactions of gravitational theory. The holographic principle and AD/CFT duality play crucial roles in resolving the information paradox in black hole theory and in constructing theories of quantum gravity. Additionally, they provide powerful tools for studying strongly coupled quantum field theories. The holographic principle and simulation hypothesis are related theories. The holographic principle suggests that information about the volume of space can be encoded on the boundary, such as the gravitational horizon of that space. Proposed to address the black hole information paradox, it implies that information about matter consumed by a black hole is encoded on the surface of its event horizon. The simulation hypothesis posits that our universe could be a simulation of some intelligent entity, with the existence of minimum and maximum units in the universe. It is associated with the holographic principle as both theories involve limits and phenomena reminiscent of quantum mechanics and computer operations. In other words, the holographic principle proposes that the universe is a 2D projection, while the simulation hypothesis argues that the universe is a simulation run by a computer. Both theories fall within the realms of physics and philosophy, presenting hypotheses that are challenging to scientifically validate or refute. Regarding the fate of an object falling into a black hole, the answer to whether it will undergo complete collapse is as follows: an object falling into a black hole does not undergo complete collapse. An object beyond the event horizon of a black hole is drawn towards its singularity due to the black hole's gravity. The singularity is a region where gravity becomes infinite, and spacetime is warped, violating known physical laws. Therefore, An object falling into a black hole will exist in some form at the singularity. Hawking radiation is the energy emitted from the singularity of a black hole. It arises due to quantum effects, and as the black hole's mass decreases, it emits this radiation. Hawking radiation is not emitted as a thin beam but is composed of various particles such as photons and neutrons. While there is a possibility that an object falling into a black hole could be expelled through Hawking radiation, it does not necessarily mean it will exist solely in the form of Hawking radiation. In more detail, an object falling into a black hole may exist in two possible forms at the singularity. Information form. The black hole does not violate the law of information conservation. Therefore, information about the object falling into a black hole should be preserved at the singularity. However, the nature of this preserved information in the region where known physical laws do not apply is yet unknown. Material form. The black hole emits energy through Hawking radiation as its mass decreases over time. Consequently, there is a possibility that material could be expelled from the singularity at the moment of the black hole's complete evaporation. However, whether this material retains the original form of the object falling into the black hole remains uncertain. In conclusion, the specific existence form of an object falling into a black hole has not been conclusively determined. It is anticipated that further research will provide more information on the nature of these objects through ongoing scientific exploration. An object falling into a black hole does not undergo complete collapse, forming a thin stream like Hawking radiation that doesn't escape. As the object approaches the black hole, its size diminishes and compresses due to the immense gravitational force. During this process, the object's energy is converted into heat and kinetic energy, emitting from the black hole, a phenomenon known as Hawking radiation. Hawking radiation plays a role in gradually reducing the mass of the black hole. If the mass of the black hole decreases sufficiently, it could eventually lead to the complete evaporation of the black hole due to Hawking radiation. However, an object falling into a black hole does not completely collapse into a thin stream like Hawking radiation and doesn't get expelled outward. The information of the object is stored inside the black hole, and the energy emitted through Hawking radiation does not contain the information about the object. In other words, an object falling into a black hole doesn't entirely disappear, it exists in a stored state within the black hole. The specific form of existence inside a black hole has not been definitively clarified. Some scientists argue that a singularity exists inside a black hole, and the object is absorbed into this singularity. Others posit that there is no singularity inside a black hole, and the object spreads throughout the internal space of the black hole. This problem remains one of the yet-to-be-solved puzzles in physics. The scientific claims or theories regarding black holes serving as gateways for time travel, different dimensions, or other galaxies are as follows. Time travel using black holes. There is a proposition that the powerful gravitational field near a black hole could be utilized to achieve time travel to the future. This idea is based on Einstein's special theory of relativity, which explains that time for an object moving at speeds close to the speed of light passes more slowly than for a stationary object. The intense gravity near a black hole, which is so strong that even light cannot escape, would cause time near the black hole to flow much more slowly than in the external environment. Therefore, a spacecraft passing through the vicinity of a black hole might arrive in the future, from an external observer's perspective, after thousands or even billions of years have passed. Wormholes connecting black holes and white holes. The hypothetical concept of wormholes suggests that a virtual passage connecting black holes and white holes exists, allowing for travel to different spaces or times. Wormholes are theoretical pathways that enable rapid transit from one point in space to another. In this scenario, the entrance of a black hole is connected to the entrance of a white hole. Black holes act as objects that pull matter in, while white holes expel matter. Theoretically, through a wormhole, one could traverse to other galaxies, dimensions, or even different times if the entrances exist at different temporal points. However, wormholes are considered highly unstable, and their lifespan is short. If a wormhole contracts, it would destroy everything passing through it. 3. Black hole singularity connecting to other dimensions. There is a hypothesis suggesting that the singularity at the center of a black hole, a point with infinite density and curvature, might be connected to other dimensions. The singularity is a region where the laws of physics, as described by general relativity, break down, requiring a theory of quantum gravity. According to some theories, the singularity may be linked to spatial dimensions other than the three we observe, and traversing a black hole could lead to other universes or dimensions. This hypothesis is related to theories like brane world theory or M-theory, which deal with higher dimensional spaces. It is important to note that these scientific claims or theories regarding black holes as gateways for time travel, different dimensions, or other galaxies have not been fully proven, and further research and discoveries are needed. This area remains speculative and unproven in scientific terms. Einstein and Rosen published a paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" in 1935. In this paper, they introduced the concept of a hypothetical passage called a wormhole, connecting black holes and white holes. A wormhole is a theoretical pathway that allows for rapid transit from one point in space to another, assuming that the entrances of a black hole and a white hole are connected. Black holes act as objects that pull matter in, while white holes expel matter. According to this theory, it was claimed that traveling through a wormhole would enable movement to different spaces or times. In other words, an object crossing the event horizon of a black hole could exit through the entrance of a white hole, potentially allowing for time travel. However, this theory has not been substantiated by scientific evidence. The existence of wormholes appears feasible under general relativity, but it encounters contradictions with quantum mechanics. Additionally, wormholes are highly unstable, and their short lifespan raises the possibility of destruction for anything passing through them. Therefore, the feasibility of time travel through wormholes remains unknown. The black hole information paradox refers to a contradiction between the predictions of general relativity and quantum mechanics regarding black holes. According to general relativity, black holes pull all matter and information beyond the event horizon. The event horizon is the boundary from which even light cannot escape. In contrast, quantum mechanics dictates that information must be conserved. Therefore, the fate of matter and information pulled into a black hole becomes a problem when the black hole evaporates, causing the event horizon to disappear. If all information inside the black hole is destroyed when it evaporates, it would violate the conservation of information law. On the other hand, if the information inside the black hole is preserved during evaporation, it implies the possibility of information moving beyond the event horizon, contradicting general relativity. In summary, the concepts of wormholes and the black hole information paradox remain speculative, lacking definitive scientific proof. The questions surrounding the feasibility of time travel through wormholes and the fate of information inside evaporating black holes are yet to be fully understood. Therefore, the black hole information paradox presents a fundamental challenge to our understanding of black holes. Various attempts have been made to resolve the paradox, but a definitive solution remains elusive. One proposed solution suggests that information swallowed by a black hole is preserved at the singularity. The singularity is a point at the center of a black hole where gravity is infinite and spacetime is highly warped. Since our known physical laws do not apply at the singularity, it is suggested that information could be conserved there. Another solution proposes that when a black hole evaporates, the information inside it is emitted in a copied form. Hawking radiation is the energy emitted when a black hole evaporates, consisting of various particles such as photons and neutrons. Therefore, the information absorbed by the black hole might be copied into these particles and emitted. While the black hole information paradox remains unsolved, it serves as an essential research topic to expand our understanding of black holes. The paradox revolves around the fate of information swallowed by black holes, challenging the application of both general relativity and quantum mechanics to black hole scenarios. The paradox emerged in 1974 when Stephen Hawking presented his paper on Hawking radiation. This phenomenon suggests that black holes eventually disappear as they emit copied energy, causing a reduction in mass. Hawking initially claimed that the information absorbed by the black hole would also be annihilated in this process. However, the conservation of information law dictates that information cannot be destroyed. Thus, Hawking's assertion that the information within the black hole is entirely annihilated contradicts the information conservation law. The black hole information paradox remains an unresolved mystery. The question of whether one of the laws needs to be abandoned or if a new set of physical laws that satisfies both can be discovered remains unanswered. The resolution of the black hole information paradox holds significant implications for our understanding of the fundamental laws of the universe. Its resolution could lead to substantial progress in our comprehension of the nature of the cosmos. Several possible solutions have been proposed to resolve the black hole information paradox. Information is emitted through Hawking radiation, Hawking copying, but remains at the singularity. This solution satisfies the conservation of information law but contradicts observational results of Hawking radiation. Information is emitted through Hawking radiation and reconstructed at the singularity. This solution aligns with observational results of Hawking radiation but violates the conservation of information law. The combination of general relativity and quantum mechanics is incorrect. This solution implies the need to discover new physical laws. The definitive answer among these solutions has not yet emerged. It is expected that future research will contribute to resolving the black hole information paradox. The black hole information paradox arises from the apparent contradiction between general relativity and quantum mechanics in explaining black holes. According to general relativity, black holes create singularities in spacetime, trapping anything that enters them forever. In contrast, quantum mechanics dictates that information must be conserved, suggesting that information from objects entering a black hole should be preserved somewhere. Combining these theories leads to the conclusion that information from objects entering a black hole must be conserved within the black hole's interior. However, the interior of a black hole is an area where the known laws of physics do not apply, making it unclear how information is preserved. The black hole information paradox remains an unsolved problem, and resolving it may require the development of new physics laws that integrate general relativity and quantum mechanics. The black hole information paradox can be divided into two hypotheses. Information is destroyed. This hypothesis suggests that information within a black hole is destroyed, meaning that when a black hole evaporates, the information of objects it absorbed is permanently lost. This contradicts the conservation of information law and is not widely accepted by physicists. Information is preserved. This hypothesis proposes that information within a black hole is preserved in some form. Consequently, when a black hole evaporates, the information of the absorbed objects returns to the universe in some way. While this adheres to the conservation of information law, an explanation is needed for how information is preserved within the black hole's interior. The black hole information paradox remains one of the most significant challenges in cosmology. Resolving this paradox may necessitate the development of new physical laws, possibly involving quantum gravity or other theoretical frameworks. In the cosmic tapestry, where black holes dance, a mysterious rhythm, a celestial trance. Gravity's grip, a cosmic embrace. Bending the fabric of time and space. On the event horizon, where light takes a bow. Whispers of secrets, only the cosmos can endow. Time travel's mirage, a tantalizing notion. A voyage through epochs, a poetic potion. Through the wormholes of uncertainty we delve. Into the past, future, where mysteries swell. The horizon's paradox, a puzzle unsolved. In the vast universe, our questions evolved. Celestial bodies, storytellers of the night. Witness to eons, in their silent flight. The enigma of existence, a timeless quest. In the cosmic symphony, we are but a guest. Parallel universes, mirroring our plight. In the grand theater of the infinite night. Beyond the stardust, where dreams and reality blend. We chase the echoes of time, around the cosmic bend. So, let us marvel at the black hole's eye, where the past and the future entwine and fly. In the celestial theater, where mysteries unfold. We dance with the cosmos, in a story yet untold.